In the previous lecture, we produced our remnant beam and scattered radiation. Welcome to RadSound FRCR Physics. We started with the source, then to the patient, to the signal, image formation, optimization, and subting. Let us optimize our remnant beam by removing scatter radiation. The journey is not yet complete. So look at the remnant of the beam, a mixture of primary photons and unwanted scatter. That's forward scatter reaching the detector. We cannot control the primary or the every event or every interaction occurring inside the patient, but we can control the beam. We can control the beam before it reaches the patient around this area. We can control what is happening within the patient. And when the beam left the patient, we can also try to control, optimize it so that we can have better image at the detector level. So that image, okay, so it's a photon going through the patient. So we may not have impact on what's going, but we can be able to do certain things, so them an image geometry, have better image. So the patient, what shall we do? So the full control point first, before the patient, we can add filtration to the beam coming toward the patient by removing the less energy, absorbing them using certain material that can absorb them, then so that we can have a better high intensity beam reaching the patient. We can do collimation, collimate the area that is capturing the patient, compensation filter such as bow tie filter in CT, playing with the KBP and the MAs. So what about now, like at the patient level? So at the patient level, we can do something. We can do compression, such as in braced in mammogram, immobilization, centering the patient also. Very important. So now let's take a look after the patient. So what can we do after the patient? So after the patient, we can place a grid, air gap, or detector positioning. We can do something by looking or taking, considering the tool, the focus spot, the part that we measure within the main anode. The focus spot can play with it. We can take smaller focus spot in the expense of Hill effects, because smaller focus spot will lead to increase or worsen the Hill effect. So we can use small focus spot for better resolution, less geometric unsharpness, or we can just do a maneuver subject to image, source to image distance, source to object distance, object image distances. We can just play with them so that we can have better image, while in the expense of certain other parameters that we'll discuss later. So now let us talk about filtration. So what's happening with the filtration? So normally filtration, the photon coming in number, mostly it affects polyenergetic photon coming from the source. So we got X-ray, that's polyenergetic X-ray spectrum coming from the source. Low energy photon contribute mostly dose to the patient with the hours in the detector, because they have low energy. So we add aluminum because we have inherent filtration, which is mostly, as we mentioned before, mostly because of the tube, because of the oil, because of the window, envelope, and others, the housing. Okay, so we have added filtration, that which will give us total filtration. So total filtration equal inherent plus added filtration. So now, as the added filtration happens, the number of the X-ray photon coming out the source would decrease. So we have, because of the absorption of the low energy, we mostly use aluminium. So the minimum amount that we add for aluminium, mostly for the glass ranges between the 2.5 to 3 aluminium millimeter. So okay, this will lead to increase the mean photon energy. This is the photon energy. So the mean photon energy will get increased from this part, this small, this lower part, to here, so that the mean photon energy will increase, but the maximum energy of the photon, the maximum energy here, will be the same, so unchanged. At the same time, this will decrease skin dose of the patient because of this amount of the energy, or the amount of the photon that has been removed. And remember, the half value layer in the previous lecture. The half value layer is inversely in relation to the linear attenuation coefficient. So meaning that half value layer equals energy over atomic number by density. So the mean energy increased, meaning that the half value layer is going to increase. So, for example, the increased or added filtration increases mean photon energy without change, or the maximum energy remain unchanged. So we have uniform added filtration, which is filtration such as the one we added with the aluminum millimeter, and we have compensating filtration, as I mentioned, such as a bow tie filter. So the bow tie filter with the body, okay, we have a body, for instance, there is a human being, there is a person inside. So we added something, a bow tie, okay, something like this, to thicker periphery and thinner part in the middle. So that will help us to maximize and equalize the amount of photon reaching the body part from the peripheral to the central part. What can we do to the beam portion of the patient? Okay, so like we get into collimation. So what is the essence of doing collimation or collimating the field view? The main collimation is like using lead shutters in the light beam diaphragm to restrict radiation field. Okay, so the light field irradiates more tissue. So instead, as for instance, now we are capturing a part of upper limb, one upper limb. So instead of capturing the whole part, more that is more larger area, produce more scatter, reducing contrast, increasing patient dose. So we get closing the collimator so that we can reduce the irradiated volume. So less tissues get exposed, gonna be less scatter is produced. Contrast as we decrease the tissue, so it will be less scatter, okay, less tissue, less dose. So collimation reduces scatter production, and the grid cannot replace correct collimation. Electronic cropping mostly will help with the change in the display, but not a radiator field to improve the remnant beam after the patient's compression. So compression, as you can see, what compression is doing. So compression, so before compression, we have greater thickness, more attenuation, more scatter, larger object image distance. So after compression, okay, less beta sharpness, reduced object image distance. As you can see, you can have less attenuation, less scatter, reduced thickness, and beta image. And in the overall, the scatter will be less and the beta sharpness of the image. And in the end, we have beta remnant beam reaching the detector. So the compression must be mostly clinically appropriate, safe, tolerable, and used only when justified. So mostly in the mammogram. So let's say we can use a selective method of scatter rejection, which is grid. So we can apply grid for scatter to select some the main primary beam and absorb scatter. So what's grid? So mostly grid sits between the patient and detector. It contains light strips separated by radiolucent interspaces, mostly made of aluminium, sometimes plastic, and others. So the importance of grid, where mostly like primary photons mostly is traveling approximately perpendicular to the space. So we have light strip here, we have interspaces, okay, made of low attenuation such as plastic and others. So get let's trace the primary beam passing perpendicular was passed through the interspaces, whereas the scatter oblique is going into this direction oblique, okay, will get absorbed by the lead strip. So the grid does not stop scatter being created inside the patient, because we are now discussing how can we optimize the quality of the primary or remnant beam reaching the detector after leaving the patient. So it reduces scatter reaching the detector, but it does not affect the scatter coming from the patient. So grid, let's talk about grid ratio, which is very important. So grid ratio is the, like we take the height, okay, the height of the light strip, okay, over the weight between the of the interface, the weight. So now equal h over weight of the interspaces. So this is what we call grid ratio. So ratio must be between 6:1 up to 18:1. So what's that? So the high grid ratio means beta scatter rejection and but at same times greater exposure, so high dose. Meaning if you are using high grid ratio, it will lead to high dose exposure and mostly more position sensitivity. So this is the disadvantages of using grid. Most of it will get observed, and only the one passing perpendicular will pass through the interspaces. So now, okay, so what is Bucky factor? It means the incident, the ratio of incident radiation, okay, falling on the unscattered grid, everything, the incident radiation. So that incident radiation that could be from the scattered one, okay, scattered photons, or from the main primary beam. So the ratio of all of it against the main transmitted primary radiation or primary photons. So means incident radiation over transmitted radiation, or exposure of the grid over exposure of the outgrid, or MAs, the current with the grid, okay, then exposure necessarily to produce the image quality with the grid over exposure that will produce same image quality with the outgrid. This is what you call a grid or Bucky factor. So you say, so let's say talk about a bit of more types of grid. We have parallel, that's a strips of parallel, as we mentioned before. We have focus, the strips of towards the focus spot. Okay, we have moving, we have stationary. So there are certain things that we have to discuss. We have something called grid cutoff errors. So let's say we have off center. This is a grid which is the tube is tilted laterally toward the grid. So in such situation, the center of the image, the center of the detector, could have image, could have information, but the pre-pro will have problems. Similarly, upside down, or what we call like inverted, focus inverted grid. So it will also have problems with the pre-pro, and the center will have some image because it is totally upside down and also inverted. So we have off focus at the off level. So off focus is a grid whereby the source to image distance is totally wrong. So it is no per the focus, it's off focus, and that will lead to problem also on the peripheral. The off level is too angled to grid, so such may lead to total loss of information of the shell. The peripheral grid types have uniformly oriented lead strip. The peripheral cutoff, mostly in the parallel grids, the peripheral cutoff increases at short focal distances. But what about the focused one? The focus grid have angle like strips toward the focal spot and must be used within specified focal range, because if it goes above that limit, that will lead to problems. So what about the moving grids? The moving grid main issue is that it might lead to it moves during the exposure, okay, and grid lines might cause some blurring, as we mentioned last time. So it's one of the disadvantages of the moving grid. So such kind of artifact by moving grid is called sometimes called Mori. So Mori. So Mori is a part of artifact like a webby part of something like webby design, something like that. So this will happen due to moving grids line appearing in the images. Similarly, the stationary grid is not moving, so also lines of that grid could be visible and lead to a kind of artifact also on the scent, especially on the image, and that may degrade the image quality and especially diagnostic quality. Therefore, grids have advantage. You think different types of the grids have advantages, but at the same time they might cause artifacts. It might lead to definitely there will be increased dosage, dose to the patient and the exposure. So grid may lead to exposure, may lead to increase dose to the patient, and it may cause artifacts. Optimize remnant beam depollution detector, and also decrease scatter is air gap. The air gap, you can say the patients will create the object image distance that will help the grid and move the detector away, a bit away from the patient. Many scatter radiation of photon now diverge and miss the detector entirely. This is in the end it will lead to reduction of scatter contamination and improving contrast. So air gap increases object image distance. Increasing object image distance sometimes, as it increases the object image distance, means you are increasing like magnification. Against the increased magnification, we may need to increase source to image distance, and that in the end, we may substitute air gap against the using a grid, but that will lead to change a bit in the geometry about exposure factors and automatic exposure control. Let's say we get increased kbp, so you get high kbp, there will be more photon, more penetration, but at the same time there will be more scatter, and also the subject contrast will go down. In contrast, when you are increasing MA, there will be photon number will go high. So that's quantity. So kbp more quality, the MA will lead to increase quantity, detector exposure, decrease noise, but at the same time it will increase patient dose. What about timing? If you're increasing timing, there'll be more blurry image because of the timing you are taking. More motion artifact or blurry, less motion if short. That's the vice versa. And at some time, as you are having less, more blurry. You may need to increase MA. That causes increase in the dose. So timing, more exposure timing may lead to increase dose to the patient, because to prevent or to counter the image to counter the image motion artifacts and get more quality, more diagnostic quality. What about the automatic exposure control? As mostly radiation exposure has been set so that it terminates on its own when when the target receptor signal is achieved. So remember, the automatic exposure control controls only the main receptor exposure, not the patient. So it doesn't change the patient dose, but rather when the target receptor signal is achieved. So there might be some issues like wrong exposure or wrong chamber selection, maybe poor patient centering. Maybe sometimes the patient has prosthesis over chamber that is protected, or large anatomy that is covering the chamber at all. Not covering the chamber also a big problems. So in the end, the exposure might increase because of the abnormal positioning or poor selection of the exposure control. Our FRCR trap is automatic exposure control, controls receptor exposure, not patient dose. Now, general geometry approach to minimize scatter and optimize the primary remnant photon. So you see, we can do magnification by we're increasing now, decreasing the source to object distance. So meaning we are magnifying the image. Oh, sometimes you can decrease the object image distance, okay, while increasing source image distance, meaning you are magnifying the structure. So what would be the implication of this? What will happen? What does that mean? You know, intensity is inversely proportional to square of distance. So as you decreases the distance by half, the intensity will quadruple. So like that. So we have magnification, which equals image size over object size. So as you go down, it decreases or increases the object image distance away. So that means the object is being closer to the focal spot, and that will mean more larger image. That will increase the unsharpness. So at the same times, increasing the object image distance will mean equal increasing the focal spot size. So it seems like just using larger focal spot. Larger focal spot means greater object image distance, means shorter source to image distance. Also, all of them will lead to increase geometric unsharpness. So remember, one of the trap from FRCR, digital zooming after display in the computer is not equal to the geometric magnification and does not improve arcade resolution. So now, as you are using smaller focal spot, part of the geometry, you have to use smaller focal spot that have better sharpness, lower tube loading, larger focal spot, greater tube loading or more unsharpness. And sometimes remember another Hill effect. What will happen? In another Hill effect, as we mentioned in lecture 1, is that and the beam is coming from the cathode, or the electron coming from the cathode to the anode target. So sometimes the X-ray coming out of the window is more intense toward the cathode. So meaning that the anode toward the other side, the intensity of the X-ray coming out of the tube is less intense. So we mostly use this to exploit the disadvantage and place the thicker anatomy toward the cathode so that we can have better beam distribution across the body part. So the thickest anatomy should be placed toward the cathode site. This is very important. So and in the end, you can say, so let's say we have our own abdominal radiography. Why we do this until the patient collimate reduce OID, suitable SID compressions, degrade shorter time focal spot, everything to get better image quality. And so you have your own filtration starting away from the patient. So you have filtration, that what you do to remove low energy photons and the photon coming before reaching the patient. So we do something before reaching the patient. We do filtration and collimation. At the level of the patient, you do proper position and the compression. Then after the beam left the patient before reaching detector, you place grid or air gap. Then sometime you apply geometry such as minimizing object image distance and appropriate subject image or source to image distance, smallest focal spot in the trade-off while you're trading off the heat loading, because larger focal spot will allow proper and better heat loading. So shape the beam, control the scatter, perfect geometry. See you in the next video.